Hi everyone, welcome back. Our final topic is survival analysis. I'm sure you're all thinking, wow, I survived biostatistics, quote unquote. But yes, we're going to talk about survival analysis. And of all the advanced methods that we could talk about, I think this is the one that's the most relevant to public health and clinical science and to epidemiology. And we're not going to do any hands-on with this. You can sit back, relax a little bit with this. I'm also not going to test you on survival analysis per se, but it is an important analysis tool because many of the studies that we design, we have to cut them off at some point. So a clinical trial, for example, even investigating the effectiveness of vaccines, we want to conclude that in a relatively short time span, long enough to show efficacy, short enough to get something to market, and also long enough to observe, any potential side effects. But we do try to design studies to be as short as possible to get the results that we need in terms of making an estimate of some sort of effect or to look at treatment effects. And this is true for more traditional epidemiological studies as well. Framingham study, which we've used some data in the heart analysis on SARS, it's kind of unique in epidemiology in that it's an ongoing cohort, and 40 plus years now, I think. We don't generally do those kinds of studies anymore, although there are some other ones. There's this health study. There's been a long study of survivors of the bombings in Hiroshima and Nagasaki. And so there are these long-term studies where we have follow-up. But most studies wrap up within some more reasonable time frame. And that's one reason why case control studies have become quite popular, is that you can take people who have disease and people who don't have disease and look retrospectively at their exposures. There's some disadvantages of that as well, in terms of any number of potential biases. However, for anything that we're following forward in time, we very often have to cut off the data at some point. So survival analysis is useful for those situations where we cut off the data and we may have partial information on some kind of outcome. So survival analysis is also sometimes called time to event analysis. And so in addition to capturing an outcome, yes, no, we actually record the time of follow-up, from the beginning of follow-up until the event of interest, or until the end of the study when their data is cut off or censored. So an outcome in survival analysis is a yes-no type outcome, but we also have another measure of time from the start of observation to the end of our observing that person. So it could be something like time to heart attack. Let's say somebody who's had a previous heart attack and we're treating them with a new drug, or we've done some kind of surgery, some sort of heart replacement. What is the time to the next heart attack? That would be an important study to do to look at effectiveness. And a lot of procedures that we do and treatments that we do have some kind of informal warranty or guarantee that you'll get 10 years out of this hip replacement, or you'll get 5 years out of this heart replacement, and we may need to do something else. So what is the time to event? Cancer remission is another example. So if somebody is a cancer patient during a study, time to different stages, time to death. In the early HIV drug trials, death was an unfortunate, very common outcome in HIV trials. And so a lot of the drugs, the outcome of interest was time to death as the outcome. And so these methodologies have been with us for a while, but they've been used primarily in diseases that have a reasonably short window a follow-up, and there's an expectancy that the outcome will occur. So in cancers, 5-year survival, 10-year survival with certain cancers, HIV/AIDS in the early part of the pandemic, survival 3-4 years or 5 years was typical. And so that was when these kind of methodologies came to be used more. We subsequently found many other applications to using survival analysis. You can even think about more social phenomenon, time, let's say for people who are released from prison or jail, say, and time to returning to jail as an outcome, with the goal of reducing, or not reducing the time, but making so that people aren't returning. Same with psychiatric discharges, time to readmission, people who show up at the ED, time to readmission, those kinds of things. So they do come up quite often. It's not conducive to all study designs, but it's very powerful. So we measure not only whether the person had the event, but the time to event. So it does require a certain amount more information. And often when we have clinical data, we have dates like date of admission or things like that. So survival analysis is fairly good now that we have those kinds of electronic data sources where we have dates and such. And we estimate that in survival time. Survival time doesn't just mean actual survival. It could just be time to event or time without the event occurring, and that's called survival time. And we look at factors that are associated with longer survival or longer time without the event of interest happening. So in case of prison reentry, time to not being in prison would be the outcome. So there's a number of applications. So survival analysis is not all about life and death, but that's kind of where it originated. So we keep the term. So this is an example of actual survival, looking at one treatment versus another. And you may have seen graphs similar to this. This is not a scatter plot. It is survival curves. And we have here 2 survival curves. And the green is the control group. This would have been without treatment. And we have the line in red is patients who are on this drug. And this is a nice visual representation of a drug being pretty darn effective. At least that's what it looks like here. So here we are at baseline. So on this axis, and it's not labeled, it should be, is time. Okay, and it goes from 0 to 35. So I'm going to assume that this is months, not years. Rarely would we have that much follow-up. Could be days, but we're going to go ahead and say that that's months or possibly weeks. In any case, this is time 0. And on the y-axis, we have probability of surviving. Okay, so at the time 0, 100% survival because the clock hasn't started. Okay, so as we move along the x-axis, time is occurring, and we start to basically count the number of events within each group, and that then becomes the proportion who survived to that point. So even after one death, depending on the sample size, it's going to dip a little bit. Okay, so this one in the control group, there was a death that occurred within the first month. Okay, in the drug group, there wasn't a death until month 6. It looks like, and it looks like there may have been 2. Okay, so you can already start to see a separation here of these 2 survival curves. And if we continue to plot this over time, you can see that this drug seems to be protecting against death. And in fact, at the time, at 24 months, so let's say 2 years, in the control group, 100% had either died or been lost to follow-up, but we're going to assume passed away, unfortunately. So in the control group, at the follow-up of 35 months, 45% of this population was still alive. So we've got this yes-no outcome, survive, yes, no. And we also have time to event. Okay, so both the groups are experiencing the outcome, in this case, death. And we can really visualize here the difference in treatment. Now, in statistics, we rarely rely strictly on visuals, and there is a statistical test that we can use called the log rank test, which really actually devolves to kind of a chi-square test. It's a non-parametric test. And it tells us whether the difference between these two lines is statistically significant. The null hypothesis would be that the survival lines are equal, or the survivor function is equal. You can see here that they are quite different. And that's what we would hope to see in any kind of intervention study. That the intervention group is not only the proportion who are surviving is greater, but even in the earlier time span, the proportion who are still alive, 70% versus 20% in this group at 18 months, quite a bit of a difference. And let's just say this is pancreatic cancer, something that has pretty high mortality. So survival analysis was originally designed for cancer treatment trials. Like many things, we find other uses for it. Statistical analysis can be somewhat siloed, and other fields will pick it up and say, hey, this is a really useful tool. I would say that many of the methods that we use in epidemiology and biostatistics evolved in the social sciences, but then now the social sciences are using some of the tools that we developed in epidemiology and vice versa. We all like to share, but it does take some time to break these silos. So you are starting to see survival analysis used in the social sciences more, even though it started in the clinic. And so whenever there is incomplete follow-up participants, we really should use survival analysis. And that's more of a nuisance issue, that we don't actually observe all of the phenomenon of interest, and we should be taking into account that we don't have complete information or complete follow-up. And so beyond the fact that it's interesting to see the pattern of time to event, we often use this in cohort and clinical trials to deal with the fact that we've cut off the data. So in this clinical trial, we don't know the survival of these folks beyond the cutoff here of 35 months. We know they were alive, but the study ended here. They're doing better than the control group, but we still have cut off, and we don't observe the rest of this trajectory, which we know eventually we followed long enough. But so we could say that this study is cut off and the data is censored, not meaning it was edited in any way, it just means it was cut off. So it's useful for that reason as well. So some things that we should consider with time to event analysis is there are some limitations as far as having to meet the assumptions of a time to event analysis. First of all, times are always positive. You can't have negative time. And so what we end up with in terms of a distribution of times is they tend to be skewed. They're all positive values, and they tend to cluster towards the beginning, and then they have a tail to the right. So because of that skewed distribution, we actually have to use non-parametric tests. And so we have less statistical power in some cases, and there's other things that we have to, assumptions that we have to be mindful of as we use it that kind of go beyond this course, but we can't just plug anything into a survival model, I guess is the message. We have to be careful that our data is set up correctly. And so we have incomplete follow-up information, which is often the case. And so that's actually a benefit of time to event analysis, is that we do have incomplete follow-up. Now, that doesn't mean that we have necessarily missing data. It's just that we've lost someone to follow-up. So we have continuous information. We don't have gaps in between the beginning and the end of our observation of them, but at some point we lose follow-up on it. So we can count things like number of events per person time of observation, as long as we meet certain assumptions about how likely it is early versus late. One of the assumptions is that these lines here, if we're going to get some kind of estimate of the effect, are proportionate, meaning that they're not, the lines here aren't crossing, that the distance between these two lines remains fairly stable over time. And it's similar to like a linear assumption in that based on our graphical representation, it seems like it's a reasonable summary of what's happening. If these lines cross, that would mean that, well, early on, there was better survival, and then later there wasn't. And so you would need a more nuanced approach. But in this case, we can just say, hey, what's the difference between these two lines? Okay, so we often have dropouts in studies. People opt out, they die, they have other events that prevent them from having the event of interest, or the study ends, in which case we say the data is censored. And so we have this follow-up time, which is useful. And so we know that the follow-up time is less than the actual survival time. It can't be greater than the survival time. There may be survival that we don't observe, but we have them during that time of study. And so if we're making comparisons between two groups, as long as there's not some sort of systematic bias in survival times that have nothing to do with the treatment or what it is that we're looking at, then we can compare them. So let's look at an example here. And this is where we have a study that is taking in different participants, and we're looking at their follow-up over 10 years. So patient one, we didn't start following until year one. So baseline of the study was here. So these have been enrolled right at the beginning. This patient was enrolled, okay, and at 11 months, they were still alive, did not have a, in this case, we're looking at a heart attack, and that's as long as we observe them. So for this person, we have this much person time, and they didn't have the event. In this case, we started observing this person at baseline, and in year 4, they had a heart attack, okay? So we have time till heart attack in this case. This one started at year 2, had a heart attack in year 11. We have a few that were followed and dropped out. We have another one that had a heart attack. So we've got 3 events of interest. We've got 3 people that dropped out. And then we've got quite a few here for we have a full 10 months of follow-up. Okay, so we can push that and effectively say, we're starting everybody's clock at the time that we observe them, and then how much follow-up do we have. So it's not in terms of necessarily real calendar time that everybody started at the exact same time, but how much follow-up do we have on each person. So participant 1, we have 10 months of follow-up. Person 2, we have 1 month of follow-up. And we have an MI that occurred, or acute myocardial infarction at year 1, and so on. So we just get rid of that information, shift everything that direction, and then we can then calculate time for each of these participants. So participant 1, time would be equal to 10. Participant 2, time would be equal to 1. Participant 3 would be equal to 2, and so on. So everybody gets a time in the study, regardless if they have the outcome. And then we have those who have the event of interest, MI, okay? Everyone else is censored, meaning that they didn't have the event of interest during the time that we observed them. Even with the dropouts, they dropped out, but we have this much time of follow-up on them. So we can include them with partial follow-up. They're just all censored at an earlier time point, okay? So we're capturing both pieces of information. And we can then model that to say, calculate some basic descriptive statistics. What is calculate the probability of survival at 2 years. We can calculate median survival time from this cohort. Granted, this was a pretty small cohort, but at least within the study, the median survival time for those patients was 8.5 years. And this would be a univariate survival curve. What I showed you previously was we're looking at an intervention to see how those survival curves differ. But we can also just use it descriptively to see what's happening with the patient population. Okay. And we can also, for a survival curve, calculate a 95% confidence interval around that estimate. So we can draw survival curves that way as well. It's not that informative, but it does show that there's uncertainty about where the true trajectory would fall. And so, especially if we're portraying two different survival curves, if we see those overlapping in the confidence intervals, it may suggest there's more uncertainty as far as where the true lines fall. But that's just one way of showing it graphically. Okay, so a survivorship function is actually based on numbers here that we can calculate in a table that are then plotted on a Kaplan-Meier survival curve. So what we would do is set up our data. We have our time 0. And so this table corresponds to this graph here. So at baseline, we have 20 patients. Everyone is still alive. And so we're at 100% surviving, okay? At time 1, our number at risk was still 20. We had 1 death at time 1, okay? We can then calculate our survival probability as 1 times 20 minus 1 divided by 20. So basically 19 divided by 20 times the beginning proportion that we had, which was 1.0, and get 0.950 and so on. And so our survival probability at any point here will be the probability of having survived up to that point and then at the end of that time period. So we've got 95% surviving through 2 years and so on, okay? And so it's a pretty easy math here. So we create this life table, and from that we can then plot the survival curve. So you could do this actually manually. Like most things, we'll have a computer do it, but this is how those probabilities would be calculated here. Okay? And that's what we see here. So at time 24, the calculated probability would be at 0.507, corresponding to where we are on this graph here. So this could be represented just as easily in a table, but obviously a graph is a little easier to look at. And if we have a lot more time points, a graph is certainly going to be easier to look at as well. So we can use what's called a log rank test to compare the survival in 2 or more independent groups. So if we have 2 survival curves and we want to say, are these statistically significantly different? We can use what's called a log rank test, and that would be kind of our crude test of whether or not there's an association between, let's say, treatment and survival. It's a type of chi-square test that compares the observed number of events to what would be expected if the groups had equal survival. So it actually is a non-parametric test, very similar to a traditional chi-square test in terms of how it's calculated and how it's thought about. Okay, so here we would say the null hypothesis is that the 2 survival curves are equal, okay, which kind of hard to think about what a survival curve looks like, but we're basically saying that they would follow the same pattern. And so likewise with a chi-square test of independence, we would assume the marginal frequencies or the marginal percentages, that everyone had the same percentages. Here we'd have equal probabilities of dropping off at any given point. So that's what 2 survival curves being equal would look like. So the same value of the chi-square test, 3.84 would be the rejection. In this case, we have a chi-square value of 6.15. We can reject the null hypothesis. P would be less than 0.05. And these would say that the two groups are different. And so we can do a statistical test that way for just a bivariate analysis. And the nifty thing is if you're doing a PowerPoint presentation, you're not just saying it's statistically significant, but you can actually visualize here what's happening between the two groups, which I think is one reason why survival analysis is popular. It has some visual appeal in addition to the statistical description. Just like other approaches that we've looked at so far, if there's a bivariate version, you bet there's a regression version. So there's a messy sounding things, which is Cox proportional hazard regression or Cox proportional regression or just Cox regression. You'll see it written all three different ways. But basically a Cox model is used for a statistical adjustment in survival analysis. And just like we need a logistic regression to go beyond using a 2x2 table, regression is more powerful. And so we use Cox proportional hazard models to model these different survival curves. So what we can do is we can actually get adjusted survival curves for covariates. And what's kind of neat is that we could actually plot adjusted survival curves. So if we age adjust, we might see that the two curves become closer together through the adjustment. So that's kind of nifty as well. We can visualize the effects of confounding. We can also stratify and do other things as well. So Cox proportional regression, Cox proportional hazard regression is kind of an advanced technique. However, it follows some of the same rules as linear regression and logistic regression, and our interpretation of the coefficients is actually most similar to logistic regression, as we'll see here in a moment. So the model itself is the log of the hazard ratio of the outcome. And hazard has to do with kind of the instantaneous risk of experiencing the event of interest. So over time, kind of what is the average risk of dropping out or of death. So technically what we can then get out of a hazard model when we take raise the exponent of e to the coefficient b, we get the hazard ratio instead of an odds ratio. We can interpret a hazard ratio similarly to an odds ratio, which is similar to a relative risk, where above 1 equals increased risk or increased likelihood of event. Lower than 1 means diminished risk, protective effect, and so on. So they're fairly interchangeable in terms of interpretation. The language we use around them, we have to be careful. So odds ratios, we really should be saying the odds of the event are more likely. Hazards ratio, we would say the hazard. However, we can often just say risk, whether it's appropriate or not. So here's an example of using Cox regression. This comes from the Framingham study. Now the Framingham study is still following people, but if we're going to do a study using the current cohort, we might use survival analysis knowing that we have partial follow-up on people who are still living. So our outcome here is all-cause mortality. That cohort is getting old. And so we have quite a few participants who are in that study and are now over age 45. Many of them started in their 20s. We have 10 years of follow-up, and we're going to now analyze this with Cox proportional hazards model. So this is what a Cox regression model using the Framingham study would look like. It's a lot like a logistic regression model. Our outcome is all-cause mortality, and we get coefficients, our betas here. Again, not directly interpretable, except that a positive value, even though they're very small, positive value would translate into an increased hazard or increased risk. And all of these are statistically significant. Age, being male, systolic blood pressure, being a smoker, higher total cholesterol, and having diabetes. All are associated with mortality in this cohort. So why do we know that high blood pressure is not a good thing? How do we know that smoking is not a good thing? How do we know that cholesterol is not a good thing? Diabetes. Some of our earliest evidence actually came from this Framingham study. Now, obviously, there's been lots of other studies that have been done, and all the way down to pathology studies and studies on rodents and all kinds of things. But in terms of human evidence, Framingham has shaped a lot of what we know epidemiologically about associations, ones that we kind of take for granted now because there's been so much both media and popular attention to these factors. Pre-1950 or so, we didn't really know a lot of these associations. It's things that we know, take for granted now. Okay, so again, we would say for a 1 unit increase in age and years, being male increases your risk 50%. Systolic blood pressure, smoking status, I think that would just be yes. If they're a smoker, 2-fold increased risk. And this is for all cause mortality. So this wouldn't be specific to any kind of cancer or something like that. The risk of specific cancers, which they actually have studied in Framingham, may be much higher for something like smoking. But this is overall mortality. Okay. For some reason in this cohort, diabetes is actually, oh, this can't be right because this must be 1.82. I'd have to exponent that, but that cannot be right because that would be positive. It would actually be close. Actually, it'd be close to 1.0. In any case, sorry about that. But the point is that a hazard ratio would be interpreted very similarly to an odds ratio or a relative risk. So summarizing across all these regression models, we've got now linear regression, logistic regression, Cox proportional hazard models. They're used widely in public health, all of them. Logistic regression and Cox proportional hazards probably used the most just because of the study designs that we use. And of those two, I would say logistic regression. We saw there where Cox models were used in a cohort study. Many of the earlier studies probably just used logistic regression. We've come to realize that there are some biases that occur because of partial follow-up. So you may use a hazard model instead of a logistic model just to deal with that issue. You're not really interested in time to event, but you want to deal with censoring. It could be more appropriate to use survival analysis in that case. But in any case, these are the kind of power tools in our toolkit. So the selection of a model type depends on the study design and the type of outcome that we have. Is it continuous? Is it time to event? Is it dichotomous? That's how we choose the tool. Just like if you were working on any project, you pick the right tool for the job. And that's why we would choose linear regression over logistic regression over survival analysis. And as a biostatistician, your job is often to recommend the statistical approach that will be used to analyze the results. And what information do you have before the study starts? Well, you decide how you're going to measure things. And you then plan accordingly as far as what tools you're going to need to use on the analytics side. Both logistic regression and Cox models provide adjusted estimates of risk, odds ratios, and hazard ratios. It's a little harder to obtain risk estimates from linear regression. We can get incidence ratios, but logistic regression is often used in cohort studies, even though technically we could calculate a relative risk in a cohort study. We often just resort to using odds ratios just because they're convenient from logistic regression. But they're very powerful tools, and just like I said before, we don't jump into the more complex analysis. We start from our basic analysis, work our way up. So in the case of survival analysis, we would start by looking at bivariate survival curves, looking at what the relationship is over time, see if the things are related to each other, the independent variables, and then that can help us decide what will go into the model. In the case of a survival analysis, we want to be even more parsimonious, meaning we want to be select fewer variables than we would other models. That's because of the kind of strict assumptions about the lines being parallel, and also that they, because it is a non-parametric test, it has less statistical power, and so we want to be careful not to include too many things in a Cox proportion hazard model compared to the other two types. But that would be not an issue in something like Framingham, where they have tens of thousands of people, or in this case 5,000 in this older cohort. So I can see the tears welling up among all of you. We are now done with biostatistics. Yay, we made it as far as survival analysis. You survived. And obviously there's so much more work that you could do to get practice with this. I encourage you to not see it as just getting through this, to see it as a really useful and powerful tool, not only in terms of your ability to understand what's going on in the world, but also just as a skill that you can offer to employers. I have found that the need for statistical analysts is always out there, and it's not restricted to medicine and public health. There's a growing demand for people in data analytics and other areas that have these same skills, and you'd be surprised how transferable this kind of analytic technique is to other human questions. Even when it comes to things like product design or business world. So all of us statisticians joke that we could be making tons of money in Vegas if we just wanted to go there. And actually, as statisticians, you sometimes get banned from Vegas. So if you're planning on going to Vegas, don't wear your I passed biostatistics t-shirt. You might not get entry. I know you're all thinking about doing that. So anyway, it's been my pleasure to be your professor for this class. I'm real excited to work with any of you if you choose to do some analytic work as part of your master's program. I would be very happy to provide advice, especially if you've collected your own data or if you're using secondary data analysis. I really enjoy working with data. I don't know if you can tell. So I would hope to impart to you some enthusiasm for doing that. So again, congratulations on making it through a difficult topic, especially within 4 weeks. But I hope that at least some of the information has stuck and has inspired you to want to learn more, not less, about statistics. So have a great rest of your summer. And I know I want to acknowledge the fact that we are all still in the middle of a very difficult time with the pandemic. And so be easy on yourselves, be easy on those around you, and I hope to see you soon. Bye-bye.